All right, I really like this problem because it's got a lot of great elements to it. There's a lot to do with it, but you might be stuck. You might not really know how to approach this. So we do know it's a boiling point elevation problem. So when we know that this equation is somehow going to play a role. So I might as well write this equation down, and we know we're going to use it somehow. And anytime we're going to use this equation, we're going to have to use pretty much all its parts. So let's figure out right now what we know. We know KB off the bat, it's given to us, and we pretty much know delta TB. They give us the boiling point, and we know water normally boils at 100, so the change in the boiling point is just going to be 0.49. So delta TB is known, it's 0.49 Celsius degrees. So that's known. So in order to do anything, I'm going to have to either know the Van 't Hoff factor or I'm going to have to know the molality. And we get molality by knowing the concentration of the solution. So we need the kilograms of solvent, got that. We're also going to need the moles of solute. Well, they give us the mass of solute, that's great, but without the molar mass, we can't really get anything from there. So right now, molality seems like it's tough to get. Now, what about I? Is there a way we can figure out that? They don't give us the formula, but they do tell us it's an alkali metal and a group 16 anion. And what do we know about alkali metals? Well, we know that they're in the first column, they form a positive 1 charge. And a group 16 anion, we don't know what it is, so let's just call it Y. We know they make a negative 2 charge. So if we figure out this formula, you'll need two x's of positive 2 to match the negative 2. So the formula will be x2y, but ultimately when this dissociates, notice there are 3 ions. So we now know the Van 't Hoff factor, and we know that that is 3. So now we know everything except molality. So you may have no idea how to approach this problem, but if we have an equation, we know everything except one variable, it makes sense to figure out what this variable is. So let's find the molality. So the molality is going to be the change in the boiling point divided by the Van 't Hoff factor times Kb. So the change in the boiling point is 0.49 Celsius degrees divided by 3 times 0.51 Celsius degrees per molar. So let's divide that. So I get 0.49 divided by 3 times 0.51. Make sure you're putting this in your calculator properly. But I will get 0.32, and this is in units of moles per kilogram or molal. I'm going to keep it as moles per kilogram. You'll see why in a second. Great. So I have the concentration. But ultimately, what can I do with that? I need to figure out the identity of this compound. And one way to identify a compound is knowing its molar mass. So if I know the mass of the solute, if I knew the moles of the solute, I could calculate the molar mass. So how do I figure out how many moles of solute are in here? Well, knowing the concentration, molality equals the moles of solute divided by the kilograms of solvent. So what do we know here? We know the molality, and we know the kilograms of solvent. We don't know the moles of solute. So let's solve for that. So the moles is going to equal the molality, moles per kilogram, times the kilograms of water, which is 0.2 kilograms, because 200 grams of water is 0.2 kilograms. So I now know that I have 0.32 times 0.2. There are 0.064 moles of solute present. So I know that, and I know that this is equivalent to 5 grams of the solute. So from that, I should be able to get the molar mass. So 5 grams of the solute over 0.064 moles. Notice the units of this are going to give me grams per mole, which is what I want. So the molar mass of this substance is about 78.1 grams per mole. So whatever my mystery substance is, it is 78.1 grams per mole. In addition, I know my mystery substance has the formula x2y, where their x is from the first column, the y is from the second column. So if I go to my periodic table, I'm looking for something, the formula x2y, which is about 78.1 grams per mole. So we look for candidates. So in this first column, I need 2 of these. So anything that when I double it is going to give me over 78 is out. So out, out, out. K is 39, which when you double it is 78. But then I'm not going to have any left over for my group 16. So potassium's out. Lithium, if I double 7, I'll get 14, so that's possible. But let's start with sodium. So sodium's 23, so 2 sodiums times 23 is 46. So that means that I have 78.1 minus 46 left over for my group 2 anion, 32.1. So I look and say, do I have one that's 32.1? This is a great candidate, sulfur. So I'm going to guess that my formula is Na2S, because this adds up to about 78.1. Now, to be safe, I could double check and say, well, is lithium possible? So 6.94 times 2. If I double that, I get 13.88. And let's see, is there a possible way to make that work? So 78.1 minus 13.88, that would give me a molar mass of 64.2. And notice there's no 64.2, so lithium won't work. And if I do the same thing with hydrogen, well, you could make a case that hydrogen might be close, because you'd have 2 from hydrogen, and you need something of about 76. Selenium's close to 76, but our best answer is still Na2S. So that is going to be our final